Thank you, Frédéric. So it's a great pleasure to welcome Matilde Marcolli here. As you see on our emblem, it was a woman who teach geometry in this picture. So it's natural to begin by a woman doing geometry. And I hope you will be happier than the people we heard on the picture. And Matilde is a professor of mathematics in Caltech. And she was mainly interested with many subjects of geometry, algebra, and physics, and especially interaction between algebraic geometry and quantum field theory. But she has a much larger spectrum. For example, I must confess, she also published, write and publish poetries and book on art, and his widest interest made that is natural in some sense. She also interested by human sciences, and which is a vocation of information theory too. And she will present us recent work applying or looking for application of geometry, algebra, and especially statistical structures she invented to computational linguistics. So the title is geometry, From Geometry and Physics to Computational Linguistics. So perhaps I go back and I come after for the question. So you have 1 hour, perhaps included question. Thank you very much.
So thanks a lot for inviting me to speak at this conference. I'm, as Danielle was saying, been mostly working somehow at the interface between mathematics and theoretical physics, geometry and theoretical physics. And so recently I also did a little bit of work in the direction of things related to information theory, which I'll talk about this afternoon in the section that Danielle and Per are running. But what I'm talking about in this talk is a topic that's a little bit different, and it has to do with somehow trying to use ideas from geometry, topology, and physics to think about a completely different subject, which is linguistics. This is something that I'd actually been playing with a little bit in the last few months, with a group of students at Caltech. And we've been trying to see with a bunch of experiments, computational experiments that I'll talk about in a moment, whether one can use methods, more geometric or topological methods, to think about the structure of language. So, I mean, I'm sure probably most of you are more familiar with the geometry side than with the linguistics side, so I'm going to go very quickly through what I mean by linguistics and what kind of problems one is interested in that setting. So linguistics is by definition the study of language, and what I mean by language is really natural languages, not artificial languages like programming languages, formal languages, and so on. It's really the human natural languages that you see around the world. And the point of view of, which is a general point of view of modern linguistics, is that language is some kind of structure. And one wants to understand what kind of structure it is. And that's the origin of the idea that the subject it may be possible to approach the subject mathematically, because after all, mathematics is, in a sense, about the understanding of structures. And so the kind of questions that typically people ask about languages is, how are different languages related? We all know that they come in families, and that we also know that languages evolve in time. Ancient languages that gave rise to modern languages, and the languages are kind of dynamical entities. And also know that people acquire languages, and their children, they learn how to speak, and we all know that it's much easier to acquire a language in that way than when you try to do it as an adult. So there are kind of neuroscience-related questions on what is the process of language acquisition, how that works, and how the structure of language is stored in the human brain. And there's, in a sense, an aspect that I'll come back to in some way, is the fact that if one looks at what has been happening in modern linguistics, one finds a kind of dichotomy between a discrete and a continuum approach. The discrete approach is to think of language as some kind of algebraic structures, and the continuum approach is the idea of the fact that these algebraic structures should support some kind of probabilistic structures, which is what is, after all, at the basis of all the mainstream sort of computational linguistics that has to do with machine translations and natural language processing and so on. And finally, as in all the sciences that have to do with human phenomena, language, there's a problem that you want to model it in a way that's not just descriptive, but that it should be predictive in some way. Right? So that's why also one wants to have mathematical models. So another thing about language is that languages are things that you can look at many different levels of structure. And according to what level of structure you're looking at, you would expect to find different kind of models. And I have this, since I'm originally a physicist, I have this analogy in mind that if you look at the world at different scales, you have different kind of physics that you encounter. And as you move the scale, I'm sure all of you are familiar with this old beautiful little movie that's called Powers of 10, where you zoom in and out by changing the scale by a factor of 10 each time, and you see that the world looked very different as you change the scale. And so something similar is happening with languages. There are basically at least 4 different levels of scale at which you can think about languages. The finest scale is when you look at languages at the level of the sounds, the basic sounds and how they are combined. That's the phonology level. But you can go further out in the scale at which you look at languages and think that the basic unit now is the word, not the composing sound of the word. And then you're at the level of morphology, where you study how words are modified by grammar. And there's a further larger scale, which is syntax, where the unit of measure is not a word, but the sentence. And so syntax is the structure of sentences in a language. And then there's a further out, larger scale, which is that of meaning, which is the semantic scale. So, and as I said, according to the level at which you want to look at languages, you're going to have to deal with different models. So I'm just going to stick to one level, and I will focus only at the level of syntax. So syntax is how sentences are produced and how they're structured. So when linguists think about syntax, the picture they have in mind is sort of like these Calder sculptures. So you think of sentences as a kind of tree structures that's hanging somewhere, and the place where it's hanging is the whole sentence, and the subtrees are the substructures that a sentence is built out of. And what distinguishes different languages is the way these trees are structured. So, for example, you can see that the tree, the part of that tree on the right and the part of that tree on the left have a different way in which the subtrees are nested. And that would correspond, as I'm going to say in a moment, to a language that's head final, like Japanese. And that part would correspond to a language that's head initial, like English. And so there's certain properties of a language that you can flip around and change and switch from the way a certain language works to a way another language works. And that's one of the key ideas of modern linguistics, that there's some kind of structure that's detected by this kind of parameter. So the basic tenet of modern syntactic theory is that, so what syntax does for you is to test grammaticality. So you produce a sentence, given a certain lexicon, and then you want to know if that sentence is grammatical or not, and whether, so there's a, it is that you have the idea of generative grammar is that you have a mechanism that produces sentences given a certain lexicon, and you have a mechanism that cuts off all the ones that are not grammatical according to the way that language is structured. And there's a kind of somewhat more metaphysical idea in modern linguistics, which is the idea of a universal grammar, which is the fact that there's somewhere, well, it's somewhat controversial because one doesn't really have evidence from the neuroscience perspective that the universal grammar really sits in our brain. But the idea would be that all these settings that decide whether a language works a certain way or another way are somehow recorded in some way in our brain during the process of language acquisition, and once they are set, we form sentences according to that rule rather than another rule. Of course, there's a question behind this idea whether this universal grammar idea that goes back to Chomsky is a falsifiable theory or not in the scientific sense, and there's some debate about that in the linguistic community. But I just want to take this point of view, which is called principles and parameters in modern linguistics, which is one tries to code the syntactic structures of different languages in a string of binary variables. And each of these binary variables is what they call a parameter in linguistics. It's like an on and off switch, which tells you whether the language you're thinking about admits a certain kind of construction of sentence or it doesn't. For example, as I said, head directionality is the one that I already mentioned. And for example, you have certain languages would put always the subject before the verb. Other languages would always put it after the verb. And each of these, in some languages, might allow you to do both. So each of these is a 0-1 choice. You either can do it or you cannot do it. And once you list all these possibilities, you get a string of binary numbers, which are the corresponding parameters. And you see the way these parameters are set, determine the kind of structure that these subtrees of a sentence can have in how well-formed sentences in that language. So there are cases, as I said, where a language has both possibilities, but one of them with a higher frequency than another one. So there's a certain sense in which linguists now think that you should consider these parameters not as completely deterministic variables, but with a kind of probability attached to them that has, that correspond to the frequency with which that parameter falls. But I will, for the purpose of this talk, really think of parameters as being just binary variables in a set. So typically parameters detect word order in sentences and other properties like whether, I'll make an example in a moment what pro-drop means, whether you can drop the subject in a sentence or not, and you can drop the pronoun and so on. And so there are problems related to this parameter model of syntax. And two of the main questions are, the first one is what are the relations? So one can list a lot of these parameters. One can list some hundreds of parameters and actually linguists have recorded a lot of these parameters for a lot of world languages. There are very nice databases that I'll mention later, which is what we use for these computational experiments. And so there are lots of these parameters, but one problem is that it's unclear what are the relations between them. So it's known that certain parameters when they are set in a certain way, will force other parameters to be set also in a certain way. So they're not all completely independent variables. However, it's not clear really what are all the dependencies. So what is a set of, a minimal set of independent variables that you can use? And another kind of problem or question is that it's known that parameters evolve in time as languages evolve. And so what is the dynamics that governs this change of parameters? So what I mean by these dependencies, let me make a simple example. So two of these parameters, for example, are called null subject and pro-drop. Null subject just means that you can drop the subject of a certain sentence in certain cases. And for example, well, if you take languages like Spanish, Italian, and French, they're very similar languages, but for example, Spanish and Italian have null subject, but French does not. And that's one of the very few parameters in which these languages differ. Mostly they are, for the purpose of syntax, they're mostly the same language, but they differ by just some small differences, and this is one of them. Pro-drop is something slightly more general, which tells you that you can drop pronouns in arbitrary sentences, not just drop the subject and something like that. For example, Mandarin has pro-drop. If I say, well, literally I'm saying, don't know, like it. When I said, I don't know, do you like it? But I can drop all the pronouns and it's still grammatically correct. Of course, it wouldn't be in English if I drop all the pronouns. Now, pro-drop controls null subject because it's a stronger property. So that's a dependency between parameters. This is an easy one because you can see it, but there are lots of dependencies that are not so easy and are not so well understood. So, how many independent parameters are there? And is there some interesting geometry in this space of parameters of languages? So, the way we try to approach this question is, first of all, get as much information as we can possibly get about these parameters. As I said, there are very nice databases that are available now online, where linguists very patiently recorded syntactic parameter for a lot of world languages. So a lot, of course, means that there's many world languages that are spoken by very small populations in difficult conditions. So not all the world languages are mapped in these databases, and not all of them are mapped completely. But typically they have is some hundred of languages, which is quite a few, but I mean, there are thousands of languages in the world, so it's not a complete list. And they have about 150 parameters recorded for these languages. But it's already a good enough database that you can try to see whether there's some structure into them. So the first kind of structure that we look for is topological structure. So what I mean by that, there's an idea of, which is quite popular these days, of using topology to study structure in data sets. So you have some kind of data, and which you can plot in some way, in some usually very high dimensional space, and you try to see ways in which this data cluster together. And of course, the simplest kind of idea is to find clusters, so like connected components around which the data, group the data together in different components. But you can do something more than that. That would be like the zero homology. It just counts connected components. But you can also see whether the data cluster around some shapes, which would give you some kind of higher dimensional homology. So more precisely, what you do is this: you have your set of points in some Euclidean space, and you use the standard Euclidean distance, and you construct a simplicial complex where you just look at the n tuples of points where all the pairs have a certain bound on the distance. So you get a family of simplicial complexes that depend on a parameter, which is your distance parameter. So it's the scale at which you're looking at this data. And you can, of course, when you change the scale, you have inclusions between these simplicial complexes. So you have induced map on homology. When you compute the homology of this kind of complexes, you see that typically you find, well, I mean, if you look at what happens with the H0, it's clear. Like when you look at a very small scale, you pretty much have all the points. If the scale is sufficiently small, each point counts as a connected component. So you have lots of connected components. As the scale grows, a lot of points get grouped in the same component. And so you have fewer and fewer components. And so you have, at the beginning, you see a lot of generators of H0 that tend to disappear after a while. And the same thing typically happens with the higher dimensional things. So you see certain kind of generators that persist for a while and then disappear, or appear and persist for a while and disappear. So this one typically represents the picture in this kind of barcode graphs where you see the generators appear and disappear, and you have these births and deaths of persistent generators. And the idea is that the longer a certain generator persists, the more it's really telling you a feature of the data and not just an accident. For example, if I go back to see this picture, you can see that if you look at a sufficiently small scale, all these, you would see a lot of circles. But if you look at a larger scale, you would see only one circle. And that one circle will persist longer than the small circles. So in a sense, that's a more, it's a more interesting feature of the data rather than small circles. So the idea is that you look for generators that what are called persistent generators that remain there for a sufficiently large interval of scales. Okay, so we tried this analysis on these languages. We took a sample of about 250 languages and more than 100 parameters. And the thing is, if you try to put all the world languages together, you get a lot of noise, but because the parameters of different languages can be very, very different. But if you start to look at language families in the linguistic sense, and you analyze the persistent topology by language families, then you start to see some interesting phenomena. So in particular, what comes out is two types of phenomena. There's persistent H0, which is like connected components, and there's persistent H1. So persistent H0 is not difficult to understand because it really does correspond to major language subfamilies within the same family. And so it tells you something about historical linguistics, the fact that certain families have branched out very early into subfamilies that remain separate and they sort of evolved their different ways, and this is detectable by the topology. Persistent H1 is more mysterious, and I'll say something more about it in a moment. So persistent H1 can occur. You can think of it as being originating by two possible different phenomena. One is sort of the Hopf bifurcation type phenomenon, or you see something that is just a connecting component, and at some point it generates a circle. And another is like a path that closes up into a circle. And these correspond to different phenomena from, if your direction is time and you're looking at the evolution of languages, this will correspond to different phenomena from the linguistic point of view. So let's look at a concrete example. So the Indo-European language family is one of the most widely studied because there are ancient texts and one can reconstruct, one knows a lot about the ancient languages as well as the modern ones. So it's one of those that are best understood. So if one runs this topological analysis, only looking at the Indo-European languages, one finds this interesting story. There's two generators of H0. And I said, that's not surprising because when you look at what they are, well, it's called Indo-European for a good reason, because there's the Indo-Iranic subfamily and the European subfamily, and they branched out very early in the history of the Indo-European civilization, and these two are the two components of the H0. Okay, not surprising. There's one generator of H1. Now that is more mysterious. What is this circle in the family of the Indo-European languages? Where is it coming from? Well, let's look at other language families. So the Niger-Congo languages, that's the biggest language family in the world, not by number of speakers, but by number of languages in the family. And so it's an interesting one to look at. And this one has 3 persistent components of H0 and no persistent H1. So this H1 is a curious phenomenon that occurs in the Indo-European languages, something to do with the history of the Indo-European languages that doesn't occur in other language families. The 3H0, again, is just the fact that the Niger-Congo languages is subdivided into 3 major language families. And the 3H0 components are the 3 major language families. That's, in historical linguistic term, H0 is clear. But so what was this H1 of the Indo-European languages that you don't see in other language families? Well, a lot of people here are probably French, so you should all have a natural guess and say, yes, it's the Anglo-Norman bridge, because as we all know, modern English, derived from ancient English, Old English, as much as it derives from French. So the tree of the phylogenetic tree of the Indo-European languages is not a tree, but it has a loop. And say, okay, that loop must be the same loop, right? Well, I mean, something should make you suspicious of this proposal of the explanation. What should make you suspicious is the fact that the Anglo-Norman bridge is mostly a lexical phenomenon. It's not a syntactic phenomenon. Language has different levels of structure. And what happened there in that historical phenomenon, what happened is that the lexicon, the vocabulary of English got a lot of influx from French, but the syntax of English was not so much affected. So, this is the natural guess, but it turns out that it's not the right answer. How do you check it's not the right answer? Well, you run the same topological analysis by only looking at the group of the Germanic and Latin languages, which is where this loop should be, where it is in the phylogenetic tree. And you expect, if it's that, you would see the H1 generator appearing here, but the H1 generator does not appear. Well, you have 2 components, which are the Latin and the Germanic, which is so syntactically these 2 subfamilies remain separate, even though lexically they were joined. So, okay, what is it then? What is this loop? Well, if some of you have had the same kind of classical education that I had with all the ancient languages and so on, you know that there's always one explanation for everything. It's always because of the ancient Greeks. So, yet again, it is because of the ancient Greeks. So so ancient Greek sits in a very strange position in the tree of Indo-European languages, because it's an isolated branch. Nothing comes out of it except modern Greek. However, it influenced a lot of the European languages, not just at the lexical, but also at the syntactic level. And so if you run again the topological analysis, but this time, well, you remove the Indo-Iranic component because it's not there that the circle is contained. It's contained in the European component, in the European component. And you also remove the Greek, ancient modern Greek, that little branch of the tree. Then what you're left with now is very interesting. The circle has disappeared. So Greek was responsible for that circle. It has gone. And the rest now has 3 connected components rather than 1. So the European part of the Indo-European family should have 1 H0 and 1 H1. Now, after you remove Greek, you're left with 3 H0 and no H1. So the picture, it's kind of like you had a circle and some kind of other coming out, and Greek sits at that vertex, and when you remove it, you get three component. Okay. It's yeah. So that's something that, okay, so what is the point that I'm trying to make? Is that you can see things that have to do with historical linguistics in a way that you wouldn't see just by thinking about historical linguistics. It's seen by the topology of the space of syntax, of syntactic parameters of languages. Okay, well, what else? So, as I said, syntactic parameters should be thought of as variables that change in time in the evolution of languages. So let's think about, for example, parameters that have to do with word order. And word order in particular, the relative position of subject, verb, and object in sentences. So here are all the possible combinations of orders. And all of them exist in world languages, but with very different distribution. Most of the world languages fit into the first two categories. And the last two categories are extremely rare. It's very, very difficult to find any language that organizes their sentences in that way. They exist, though. I mean, there are examples, but they're very, very rare. And so, actually, there's some ambiguity in how one writes parameters. One can think of these as a single parameter, but one can also think of it as a product of two different parameters. So, so sometimes these things are, if you look at the literature, some prefer one way or another. Okay, so there are these facts. So first of all, these parameters are distributed very unevenly across world languages, and also they are known to change in time. So for example, this order of subject, verb, and object, it's known that ancient Greek switched over time. So okay, let me make a first comment before this evolutionary one. So the first comment is that the relative prevalence, so the fact that some of these configurations are a lot more prevalent in world languages than others, there are two possible explanations for that. One is sort of trying to look for a neuroscience explanation, so that some of these combinations are fit better in the Broca area of the human brain than others, and so that's why they are so frequent as opposed to others. And other explanations are internal, so it have to do with the way the languages evolve in time. That some are end up being attractor points and others end up not being. So both explanations, and we don't know what is the best, but people do look for either type of explanation. And as I said, these parameters change in time. So ancient Greek switched from SOV to SVO in the period in between Homeric Greek and Classical Greek. Sanskrit switched twice because of influence of the Dravidian languages. So Sanskrit is an Indo-European language, but it's bordering with the geographic area of the Dravidian languages that have it the other way. And so in the influence of a group of languages on another language ends up flipping one of the parameters. And historically, there are recorded examples how these parameters have been flipping back and forth depending on the interaction between languages that belong to different linguistic groups. Well, English also switched between Old English and Middle English between two different forms. So now, how does one try to model this kind of evolution of parameters? Well, there's a thing I said here. If you are a physicist, there's something, it's like one of those Pavlovian reflexes that you cannot avoid. If somebody says, you have two binary variables that influence each other and they tend to align, you think spin glass. I mean, there's nothing that will prevent you from doing that, right? So as a physicist, you think this is a spin glass model. And so let's say, okay, let's try to see, how much one can fit this idea into the formalism of spin glass models. So we have this bunch of binary variables. We think of each of these as a spin, which is either up or down. So each language is a vertex of your graph over which this spin model is happening. And at each vertex, you have not just one spin, but a family with all the parameters. And as we've seen historically, dynamics that tends to modify these parameters often happen because of interactions with nearby languages. So you want to model somehow the strength of the interaction. So there's an interaction like in spin models that tend to align the spins. And what is it that measures the strength of the interaction? Well, in a sense, it's the proportion of bilingualism. The more there are people who speak two languages, the more this tends to modify the languages. And so what we did is try to come up with good data that model this. And let's say in a moment we got them from MIT's Media Lab, in a moment what they use. And so there's another thing that you want to try to fit into this model. The dynamics in spin glass models, it depends on the temperature parameter, which in a sense tells you how strong the interaction, or how much the higher energy levels are activated in the dynamics. And what is this temperature parameter? Well, one way to think of it is that, as I said, these parameters in linguistics are not really frozen. There are really often possibilities of having the two states, but with certain probability attached to it. And so that is exactly what the temperature parameter does in the spin glass models. They tell you that the spins are not frozen, that they have a certain probability of being one way or another. So one can think of the temperature parameters, how much you want to think of these spins as being fluctuating rather than being frozen. However, there's one thing that you need to do, which is the fact that there are these relations between parameters, like the one I mentioned before. Some parameters dominate other parameters. So they're not just, so if these were all independent variables, we would just have a bunch of uncorrelated Ising models attached to the same graph, and they would all evolve independently. But they're not, because parameters are not all independent variables. Okay. So, okay, so basically what we'll do is, okay, the general setting is this. You have a graph, you have configurations of spins over each vertex, and you think of the Hamiltonian as being the usual way. You have the interaction terms that tend to align the spins, and you have a kind of additional term in Ising models that tells you, whether you have an external magnetic field that tends to align the spins with this field. And the reason why I'm considering this model is because I want to use a modification of that term to model the relations between different parameters. So it will be something that the Hamiltonian I'm going to consider will be something that when you freeze one of the parameters, it will look like this external. So a frozen parameter will act like an external magnetic field on the other parameters. And if it's not frozen, then it will become an interaction term. Okay, and what one normally does, there's a partition function. This determines a Gibbs measure on all the configurations of the system that weights the states. By the ground state is the dominant one, and the higher temperature states are weight depending on the temperature parameter. At high temperature, they contribute more. At low temperature, the ground state is the dominant one. And the typical picture in the usual Ising model is that there's a critical temperature with a phase transition. Above the critical temperature, there's zero magnetization, so the spins are distributed randomly. And below the critical temperature, you have this spontaneous magnetization where all the spins align in one direction. So, okay, what we're going to do is, think of a graph where all the vertices are the different languages that you can consider, and you have an edge whenever two languages interact, in the sense that there's some some amount of bilingualism measured in some way, and So you have either, you put a 0, 1 or plus minus 1 value for these parameters, or you allow the possibility of having 3 values where the 0 value is just where the parameter is not defined at all. So the reason for that is that there are situations where you have 2 parameters that are dependent on one another. This is what linguists call entailment relations, where if one of the parameters is set one way, the other one can be up or down without problem. But if the first parameter is set the other way, then the second parameter is simply not defined. So it has this 0 value. So when you have a coupling of parameters, in a sense, you're trying to couple a Ising model with 2 states, which is the dominant parameter, and the pot model with 3 states, which is the other dependent parameter of the entailment relation. And so the way we model the interaction strength, so the MIT Media Lab had constructed, they call this global language network, where they try to evaluate the amount of bilingualism, and they did it in 2 ways. So one is to count the number of book translations between 2 languages, and the other is to count the amount of Wikipedia edits. What they mean by that is whether the same editor is likely to edit in 2 different languages as a measure of bilingualism. We try to use both things, and the results are kind of the same, so they are pretty consistent. So this gives you, the strength of the interactions between this graph. And so okay, let's first do like a simplified model where you first think of the parameters just being independent. So if you think of them as just being independent, then you just run the usual Metropolis Hastings algorithm for to find the equilibrium configuration of the dynamics. So you do it's really like a steepest descent method to get to the, oops, sorry. Okay, so let's just take an example. If you just take one parameter, for example, the subject-verb parameter, which means your language allows subject before verb. And the point is that if you look at most languages have this parameter up. So most languages allow that. The only one in the database we use, the only ones that have it the other way, are the ones that have to do with the Irish, Welsh, Gaelic. It's that group of languages that don't allow subject before the verb. So it's, in a case like this, if this parameter is completely independent and everything else, it's clear that if you are in the sort of low temperature regime, the fact that most parameters are up will tend eventually to pull the other ones up. However, if you are in a high temperature situation, you can get configurations where you have a much more mixed equilibrium position of parameters. And if you, however, also encode the relations between parameters, so I just took a simple example, a very small group of languages that have an interesting configuration of parameters. So these strong deixis and strong anaphoricity have to do with how pronouns are used in sentences. And strong deixis is something that allows you to, like for example, if I say, I don't know, you like reading, and I said, reading, that's what you like. I'm making that kind of emphasis on the subject. Some languages have this kind of constructions and some don't. That's called strong deixis. Anaphoricity is when a pronoun refers to something back in another part of the sentence, and whether that same kind of structure carries over to anaphoricity from the principal part depends on the language. So, but the first parameter dominates the second. So what happens is that if the first parameter is up, the second parameter can be either way. And there are examples where it's one way or the other. For example, Russian has it up, up, and Bulgarian, which is a very similar language, has it up, down. But if the first parameter is down, the second parameter is just not defined. Doesn't even make sense to define it. So that's the -1, 0. Like Welsh has it. So if you let's just take a simple example, very small graph with this initial configuration of parameters. And now with the Hamiltonian that has this coupling of the parameter that favors this kind of configuration, where one of the position forces the other one to be either way. And so, now they're not independent variables, so if you run the dynamics now with this kind of Hamiltonian that also has the interaction between the entailment relation between the parameters, and there's like an energy scale that tells you how strong that entailment relation is. You still think of it as in a kind of probabilistic sense. It's very likely that it's enforced or it's not, depending on this energy scale. And you run again this kind of Metropolis-Hastings algorithm, and you find that you get different equilibrium configurations according to, now you have two parameters, the temperature parameter and the strength of this entailment relation. So high temperature, high energy, high temperature, low energy, low temperature, high energy, and low temperature, low energy, you find very different equilibrium configurations for this set of parameters. So this is the kind of picture that you get for the average magnetization in this case. So of course, this is like a toy model example because I took a very small group of languages, and one would have to scale it up to a much larger to have a realistic picture. Because these languages do not just interact with each other, they interact with all the other languages. So but this is the kind of idea about how one can try to model how syntactic parameters change by effect of interaction between languages. So another thing that I want to mention briefly has to do with this different distribution of linguistic parameters. I said some parameters are very frequent among languages, are very frequently activated or up positioned among languages, and others are very rare. And this also relates to, so we're trying to see how prevalence, cross-linguistic prevalence of parameters is related to possible interactions between parameters. So the way we approach this question is by, again, using the same databases of parameters and using models of sparse distributed memories. So Canerva networks are a way to model human memory, as a way to model associative memories. Mine, and it was introduced in the 80s, a model for possibly artificial intelligence. And basically what you do is you have some large space, some large vector space over F2, and you have a sample of locations in this large space, which should be sparse. So it's important that K is 2 to the K is significantly smaller than the dimension of the space. And you look at the Hamming spheres of a certain radius around all these locations, this hard location. And you have a writing and reading to memory mechanism. So given as a datum, which is a vector in your ambient space, each of the hard location gets its coordinate incremented depending on the corresponding entry of your storing datum. And when you read at a certain location, you read by the majority rule of all the locations in its access sphere. So it's, the point is that if these are sufficiently sparse, then there's not many overlaps between the spheres, so you get a fairly precise reconstruction of the datum. So the point is that Canerva networks are good at reconstructing corrupted data. If you have a small amount of your data that gets corrupted, they are stored in sufficiently well in the network that you can reconstruct the corrupted part from the remaining part of the data. And for this reason, it's also good to detect dependencies among sets of data, because you can see that certain parts of the data can be better reconstructed from the rest. And that's is a signal of the fact that it may be some kind of dependence between the rest of the variables and the one that you're constructing. So what we did is just put all this data of syntactic parameters of languages in a Canerva network. And we did it for a sample of just 21 parameters, right, for 165 languages. And then you just corrupt one parameter at a time, and you check how well the Canerva network reconstructs that parameter from the remaining ones. And what happens is that you find two phenomena. So this is actually the specific syntactic parameters that we used and the corresponding frequencies in the group of languages that we considered. And you find two kind of phenomena. One that has to do with the frequency, so the prevalence of a parameter among languages, and another which is independent of that, and it's really some kind of syntactic relation, abstract syntactic relation between parameters. So here is what we find as the corruption feature. So the lowest ones are the ones that are best reconstructible from the remaining parameters, and the ones that are up above are the ones that are more difficult to reconstruct. And these are the prevalence of the parameters among languages. So the ones that are rarest or most prevalent tend to be the ones that are best reconstructible, but not quite. So the point is, if you take random data that have the same frequencies, you find a curve that goes somewhat like this. So it's there's an effect which is just has to do with a correlation between prevalence and recoverability, but there's an additional effect. I mean, this curve is significantly different from this curve, although it has kind of the same shape. And these additional effects are really just syntactic relations between parameters. So it detects the presence of an underlying relation between parameters. And so you find that this is an example of the different degree of recoverability when it's normalized for prevalence. So it's the remaining effect, the one that is purely syntactical, of some of these parameters. So in a sense, what you can read of these results is the fact that some parameters are, in a sense, dependent variables of the other parameters. But this is the kind of dependency that is not like an algebraic dependency, is more a statistical dependence. And so these results are done by taking all the languages that we consider are a cross-section of all the linguistic families in the world. They don't belong to the same language family. So one can probably get slightly more refined pictures by subdividing the data by linguistic families and looking at how these curves change within specific linguistic families. Because, some parameters may be more recoverable within certain families than others. So that is something that we're still looking at. And one thing that I want to mention is that since Canerva networks are good models for human memory, the possible way to think about this point of view is that you want to try to, going back to this fact that people try to understand cross-linguistic prevalence of parameters in terms of possible neuroscience models, of how these parameters may be stored in the human brain. This might be a possible method to approach that question. I want to just mention very briefly something which is still in progress. One of the questions that linguists have is phylogenetic linguistics. So try to reconstruct as accurately as possible the phylogenetic tree of a certain language family. This is very well done very well done by traditional linguistics for language families for which one has a lot of old text, like the Indo-European language, or, there are other examples. This is the Mayan language family. It's another language for which there are lots of documents that existed for thousands of years and that people can read, so that one can trace the evolution of the language through the evolution of the written text. But for most language families in the world, this is not possible because one only has the modern languages and there are no written documents that go back to ancient languages, so there's no way to just do these traditional methods of linguistics to trace the evolution of languages. So what people try to do is some kind of computational methods to produce phylogenetic trees. And one method is lexical, so you have certain lists of words, these Swadesh lists, which are words that are likely to exist in all languages that have to do with certain actions, parts of the body, things that every language expresses in some way. And you try to find cognate words and measure a distance between them. there are problems with this approach because languages have a lot of synonyms, and you might have one that matches another language, but another synonym would work better for another. So there's a lot of ambiguity, and there's a lot of false positives when you try to match by machine these languages. So what I want to argue here, let me just quickly go. I mean, there's a standard technique for producing these trees given a distance, a set of data, and encoded data and a distance. But what I want to argue is that it is be better to use as the data it'd be better to use as the data the syntactic parameters rather than using the Swadesh list, because the syntactic parameters are just binary variables that are intrinsic to the structure of the language. They don't depend on the choice of a particular synonym for a word in a set of many choices. And in fact, recently, a group of linguists have already started to check whether using the syntactic parameters can generate better phylogenetic trees than using the lexical information. And for the Indo-European family, that works very well. So it's very accurate compared to the tree that one knows from traditional linguistic methods. And so what we are presently doing is sort of trying to extend this to the rest of the database of syntactic parameters for other language families and try to compare the phylogenetic trees that we get with this method with the ones that linguists can get with the lexical method. So yeah, I'll stop here.
Thank you very much for this exposition of your research. And was a question. Well, hi. That's I know.
Hello. What is the role of alphabet in this analysis? I didn't see any role of the number of the alphabets or the alphabets.
Well, so So first of all,
you mentioned that you are focusing on syntax.
That's right. No, also alphabet, you see, is something that has to do with the written language, right? So there are lots of different alphabets in the world and so on, but most languages are not written. Okay? So if you take alphabet as a point of view in languages, you restrict your pool of languages a lot. And it's also, alphabets are kind of accidental. Even you can see it when you can have different phonemes that end up being written with the same letter. So there's a lot of ambiguity in alphabet. They're not a good way to think about languages. But primarily because they completely exclude languages that are not written. And what linguists use is this phonetic alphabet, right? There's a way of just classifying phonemes. So you can write words phonetically for any language. And that's more accurate because it just records the actual phonemes. And there's like a periodic table of phonemes that has, which it just depends on position of the tongue in the mouth. So that's pretty, it has a basis in the way the sounds can be produced. But otherwise, an alphabet is just a purely conventional set of symbols. And so it's not, from the linguistic point of view, it's not useful really. Yeah.
Other question?
Any other questions?
When you had different levels of H0, H1, and H2, and you talked about persistence structure, I didn't understand how did you define the number of the components in each category. You had blue and black, and you.
Right. So.
You know, how did you?
Yeah.
What was the criterion to
yeah, so what happens is that you have a set of data and you construct this kind of simplicial complexes where you just look at, you draw if points are within a certain distance. So for each distance you have a complex. And you compute the homology of that complex. And so what happens is that the homology changes according to the scale. And so what you see is this kind of lines where you have a generator that starts and continues for a while and then drops. So the general idea with this is that the ones that persist for sufficiently long are the ones that contain some more significant information. And so the ones that we're getting that we focus on are just the ones that continue for a large set of scales. So you see, for example, you look at the H0, you see a lot which just die out after a while, after a short interval. And those are just accidental. They just depend on the fact that when you have a small scale, they're points, so they're all, but the ones that remain contain some information. Like, for example, with the Indo-European languages, you see only, at the end, you see only two that continue. Of course, if you go to a really large scale, they will become one, because eventually the two components overlap. But the fact that two of them remain for sufficiently many scales, I mean, it really corresponds linguistically to the fact that there are these two branches of the Indo-European family that are really kind of separate. So unless you go to very large distances, they will not look like the same component. And the same thing for H1. You see a bunch of things that disappear, but then you see this one generator that continues. And so that one has something significant about it that the other ones don't have. And then that's the idea.
So I also had a kind of a Pavlovian reflex. When you were talking about the H1 generator in Indo-European languages and the Greek is like as some kind of vertex. Can we think of that as some kind of blow-up of a point that was there in Proto-Indo-European?
Sorry, can you think of that?
So if I understood correctly, there's some kind of shape like this. Mm-hmm. Okay? Right. Is that some kind of blow-up of a point?
That's right.
I mean, in European might have a point and then...
Yeah, it's something like that. Yeah, I mean, I agree. I don't have a better explanation, but you're right. Yes, no.
Sorry.
Yeah, it's quite clear how we can have the phylogeny tree, starting with algebraic topology. Mm-hmm. But can you explain a little more what is the geometry of the persistent?
So I mean, like for example, a persistent generator of H1 is really telling you that the data are sort of clustering around some closed curve, right, in your ambient space. So it's this kind of picture. Yeah, right? So
can we see for languages?
Right.
Kind of
so the
geometry.
Usually the point is, it's difficult to visualize because your data lie in some very high dimensional space. So you would, if you're lucky, in some cases you can find like a good projection onto that really visualizes the circle. And so, I know we're sort of still playing with that. I don't know if we can, but usually you don't directly see it because you're inside some space of some dimension, 100-something dimensional space. So it's difficult to act. But typically the fact that you have a generator of H1, persistent H1, tells you that there should be like a good angular coordinate, right, that parameterizes part of your set of data. And the question is, what does that coordinate mean, in terms of the data that you're trying to classify? So that's the typical question that comes out of whenever you see a persistent generator of H1. The question, what is that angular coordinate? What is it measuring? So I don't have an answer for the syntactic structure of Indo-European languages, but something is saying that there's a kind of angular coordinate that parameterizes part of the syntax of Indo-European languages. I don't know what that coordinate is and what it means, but that's what the structure is saying.
Yes, I have a question which is perhaps related to this one, because the first representation, you start with a high-dimensional space. That on each axis you put a parameter, and then you put frequencies.
Right.
So, and you told us that parameters are not independent. So,
Right.
in some sense, it's question very.
That's right. So there's really some kind of manifold in this space where the parameters lie, which should capture all the dependencies between parameters. And that's another kind of question that is, can one identify somehow this submanifold?
But also this submanifold it depends on this choice of representing the parameter. If I made mixed, perhaps I could change the topology.
Yeah, I'm not sure if that would have an effect on after all, topology is kind of resistant to reparametrization if it's really topological. But, it's certainly true that, there is, these parameters are not independent. The problem is that, some dependencies are known linguistically, but there's a lot of dependencies that are not known.
Yeah.
And that one should be able to find purely by data analysis. And so, principal component analysis, trying to reduce the dimensionality of this space. This it's another thing that, trying to understand, but so far, I don't have definite data to present yet on that. But I mean, it's one of the main questions: what is the actual dimensionality?
And it could be also probabilistic dependency, that it uses not only the mean, but more of the
That's right.
of
Yeah,
the variable.
that's
So,
right.
just a last question. Do you know this work of 10 year, which was taken by Tom and Petitot? Do you have a look at that? Because it was a tentative to use singularity and topology.
That's right. Yeah, I sort of, I don't know. Yeah, it's a good question. I don't know if that can be used for this type of analysis of doing it. Yeah. I don't know.
So perhaps I thank you very much.
Okay, thank you.